In chapter 22 and 23, we are going to be looking at reactions of aromatic systems. The first of these two videos deals with the mechanism of the reaction and how it affects selectivity of the reaction. That is sections 22.1 to 7 and 23.1 to 8. Now in the past we've said that benzene was not reactive. That's not entirely true. Benzene is less reactive than alkenes or alkynes, but it will react with sufficiently strong electrophiles. The electron-rich benzene ring can use its extra pair of electrons on one of the pi bonds to grab onto the electrophile to create a carbocation. This first step is addition of an electrophile to a non-polar pi bond, the same first step that you would have for electrophilic addition to a non-polar alkene or alkyne. The intermediate is resonance stabilized to give two additional resonance contributors shown here. Although the resonance helps stabilize the carbocation intermediate, the carbocation intermediate is it's considerably higher in energy than the benzene starting material. How this reaction differs from normal electrophilic addition is that it's not addition at all, because following the initial electrophilic addition is a second step, a proton transfer, in which a proton is removed from the same position at the benzene ring that the electrophile added, re-establishing our aromatic system. The net result is to substitute one position on a benzene ring, normally a hydrogen removed in the second step, and another strong electrophile is added in its place. Depending on the identity of the electrophile, we can substitute benzene with any variety of groups. For example, our electrophile could be the equivalent of a Br+ or a Cl+, a very strong electrophile capable of reacting with our stable benzene system. Either of these halides ions is formed from adding the halide to iron trihalide and forming an intermediate complex in which the terminal halide can leave as a halide plus. A second common electrophile is the nitro group, which is formed by adding nitric acid and sulfuric acid to the solution. In fact, NO2+ is the dehydrated form of nitric acid. It's lost one water molecule. SO3 is also an active electrophile in this reaction, formed by adding fuming sulfuric acid, that is, an excess of SO3 bubbled into water to make sulfuric acid. The final three electrophiles for electrophilic aromatic substitution are the proton, provided by a strong mineral acid in water, the acylium ion, which is like an aldehyde without its H, and any other carbocation, very normally secondary or tertiary or more stable than primary. The carbocations are formed through the so-called Friedel-Crafts reactions, in which a chlorine is removed from an alkyl or an acyl group, and you normally start with an alkyl halide and aluminum trichloride. Other sources of carbocations, such as adding an H+ to an alkene, can also provide a carbocation in solution, which is a strong enough electrophiles to react with at least some of our benzene derivatives. So any of these groups can act as the electrophile, substituting onto a single position on the benzene ring. In chapters 22 and 23, this mechanism will be explaining not only the energetics of the reaction, the fact that only very strong electrophiles can do this reaction, the fact that some electrophiles, such as the cations and acylium ions, will only react with our more electron-rich benzene rings, our stronger nucleophile benzene rings, and finally, will it help us explain why it is that certain positions on benzene rings are substituted more rapidly than others, and certain substituted benzene rings react faster than others. Benzene rings that already have a substituent on them, here designated Z, can react with electrophiles as well, and could potentially form one of three regioisomers: ortho, para, or meta. It turns out that the Z group on the ring changes the electron density on the ring and changes the ring's ability to be a nucleophile. Therefore, not all Z substituted rings react at the same rate. And anytime Z can donate electron density into the ring, it will react faster, because the ring itself is a nucleophile donating electron density. On the other hand, if the Z is pulling electron density away from the ring, it makes the ring itself a weaker nucleophile and will make a slower reaction. It's also true that different Z groups will have different regioselectivities. and for reasons based on the mechanism, a given Z group will tend to either favor ortho plus para products or meta products. The reasons for favoring ortho plus para products are similar but not identical for the other groups that prefer meta products. In particular, if a Z group donates electron density to the ring, it will activate the whole ring, but it will activate the ortho and para substitution positions the most. On the other hand, if the Z group is pulling electrons moderately or strongly away from the ring, it will deactivate the whole ring, but it will deactivate the meta position the least, so that the meta position ends up being favored. During this week, and particularly in chem activities B and C, we explore why it is that activating or electron donating groups activate the ortho-para position the most, and deactivating groups deactivate the whole ring but deactivate the meta position the least. These explanations are directly based on the mechanism for EAS reaction, and in particular for the location of the positive charge in the intermediate electrophile. Where that positive charge is most stabilized or destabilized determines the preferred sites of substitution. In the remaining parts of chapters 22 and 23, we will look at a variety of other ways to put functional groups directly onto benzene rings, things that cannot be created directly with our electrophiles. They normally start with putting one of our electrophiles, either an alkyl group, acyl group, nitro, or halo, on the benzene ring, and then converting that group to another group through a series of reactions, including oxidation or reduction or a net substitution of a diazo group. The next video will address these reactions. Finally, I'd like to use an electron density diagram to examine why some groups, or why benzene is more active as a nucleophile towards some groups than others. Here we have a picture of benzene on our left and trifluoromethylbenzene on our right. On the left, benzene, and you can see the large red area in the center. That is the nucleophilic core of the benzene ring. When you put an electron withdrawing group on the ring, notice that the electron core, or the nucleophilic ability of the ring, decreases. Anything that makes this more electron rich on the end will make it a little higher in energy to start with, so that we don't have as big an activation energy. Any group that would take electron density away would stabilize the benzene, making it lower energy so that it would have a higher activation energy at the beginning.